So for number one on test number four on transformations, we have a rotation of 90 degrees, and when the direction's not specified, we assume that it's going counterclockwise. So our rule for a 90-degree rotation counterclockwise is you take original coordinates and you switch the order and you make the original y coordinate the opposite sign. So here, if I take the original y coordinate, which is 2, and I switch the sign, it would go from being positive to negative. And then if I also switch the order, I have the point negative 2, 5. So that would be answer choice number 4, the point negative 2, 5. Okay, number 2, I'm looking for the transformation that would not carry the square onto itself. So remember, if it is going to carry the square onto itself, if it's a point, like a rotation around a point, it's going to be right in the middle if it does carry it onto itself. If it's a line, if we're reflecting over a line, then that line is going to be a line of symmetry to carry it onto itself. So we're looking for, there should only be one answer choice that does not carry it onto itself. So we're looking for the answer choice that is not in the middle or not a line of symmetry. So let's get started with answer choice number 1. So that is the y-axis, and I can already see that the y-axis is not a line of symmetry. It's not right through the middle of the square. So this is going to be the correct answer. But let's go through the other choices to see why they are correct. So the x-axis is a line of symmetry. It goes right through the center of the square. Rotation of 180 degrees about the point 10. That's right over here. That's the point 10. And that is right in the center of the square. So if we rotate around this point, since it's right in the center of the square, it is going to map it onto itself. And reflection over the line y equals x minus 1. That has a y-intercept of negative 1, so I'm going to start there, and a slope of 1. So I'm going to go up 1 over 1, up 1 over 1, and I can go 1 in the other direction as well. And notice how that is a line of symmetry. So that works as well. The only one that didn't work was answer choice number 1. The y-axis, I'll just show you again, is not a line of symmetry. That does not go through the middle. So answer choice 1 is the correct answer to that question. Okay. Sorry that the formatting here got all messed up when I downloaded it onto my computer. But we're reflecting over the line y equals x. And for the line y equals x, the rule just makes things easier. The rule for reflecting over this line is that you just switch the order of the coordinates. So the 0.23 would become the 0.32, the 0.47 would become 7.4, and negative 1.5 would become 5, negative 1. So the only one that here is an answer choice is 5, negative 1, and that is choice number 1. Okay, so in number 4, they tell us that point A, which was 1, 3, was translated, and we know translated is like left, right, up, or down. It's sliding. So it's either going to be adding or subtracting from the x and y coordinates, or you can graph it and you can see how it's moving around the grid as well. So we're told that point A, which was 1, 3, became 0.44 under this transformation, under this translation. So I see that the x coordinates increased by 3 and the y coordinates increased by 1. So this was a translation of 3 to the right and 1 up. So now that we know what the transformation is, we can figure out what point C is going to become. So point C is the 0.40. So after this, we're going to be adding 3 to the x coordinate and adding 1 to the y coordinate. So that's going to become the 0.71 under the same translation. And that's answer choice number 1. Okay, moving along. In number 5, we're talking about rotational symmetry. How many degrees can you rotate an object so that it looks like itself again, so that it maps onto itself? Remember, 360 degrees is a full rotation, and we're going to divide by the number of sides, and a decagon does have 10 sides, to find out the first time that it looks like itself when you rotate it. So 360 divided by 10 is 36 degrees. So 36 degrees would be the first time that you can rotate it and it would look exactly like itself. So since that's not a choice, we're looking for multiples of 36. So I'm going to take each answer. I'm going to divide by 36, and I'm going to see which one gives me a whole number, which one is a multiple of 36. And that ends up being answer choice 4, 252. That is a multiple of 36. It goes into 36 7 times. It's 7 36 degrees rotations. And every 36 degrees, this decagon is going to look like itself. Okay, we're told that this line is being dilated and the center of dilation is the origin. So that's really nice. The first thing I'm going to do is I'm going to put this line in y equals mx plus b form. So I'm going to do that up here because I can't see the slope and y-intercept right now. So I'm just going to add 3x to both sides. That's going to be my first step. And that is 4y is equal to 3x plus 8. And then I just need to divide everything by 4 to get the y by itself. So that's y is equal to 3 over 4x plus 2. So it's asking which one could represent the image of this line after the dilation. The only thing you have to remember here is that dilations preserve parallelism. The pre-image and the image after the dilation are always going to be parallel to each other, and parallel lines have the same slope. So the only answer choice here that has the same slope would be answer choice number 2. That is the only equation of the line that would be parallel to the original one. And notice how the y-intercept is 8 and the original one was 2. So that would be a scale factor of 4 because we know if it's centered at the origin the slopes are the same before and after the dilation, and the new y-intercept is the old y-intercept multiplied by the scale factor. So that would be a dilation by a scale factor of 4. It doesn't ask us that. It just says which one could represent the image, and that would be 2. Same slopes, parallel lines. Dilations preserve parallelism. Okay, moving on to number 9. So the center of dilation here is not the origin. The center of dilation here is point D. The easiest way to do this is graphically. When we're dilating by a scale factor of 2, what we're basically doing to make it 2 times bigger is we're doubling the distance that each of these points is from the center of dilation. So I'm just going to count how many boxes point D is from point B, and then I'm going to double that distance. So that's 1, 2, 3, and 1 over. So I'm going to go another 1, 2, 3, and 1 over. And that's going to be B prime. And sorry, it's a bit messy here on the computer, but that would be the point -1, 1, 2, 3, 4, 5, 6, 7. Let me recount that because this is a bit messy here. Let me zoom it in so I can do this a little bit neater. There we go. That should be easier. Yeah, let me try. Oops. That again. 1, 2, 3, and 1 over. 1, 2, 3, and 1 over. Right there, that's B prime. And that's a little bit neater. So that is the point -1. 1, 2, 3, 4, 5, 6, 7, 8. -1, 8. I'm just going to write this on the side. -1, 8. Okay. Now I'm going to do point C. So from the center of dilation, that is 1, 2, 3 to the right, and 1, 2, 3 down. So I'm going to move another 1, 2, 3 to the right, 1, 2, 3 down. Doubling the distance. 1, 2, 3, 1, 2, 3. Just making sure I counted that correctly. Really messy on the computer. So that is the point 1, 2, 3, 4, 5, 6, 7, -1, -2, -3, -4. And then finally, I just need to find A prime. So 1, 2, 3 to the left and 1 down. 1, 2, 3 to the left and 1 down. And that would be A prime. -1, 2, 3, 4, -5, 0. And if I connect this together with my straight edge, let me get a different color, all these points, it should be double the size of the original. There we go. So that would be our dilated triangle. It's much easier to do it graphically. A lot of people were subtracting from each of the points the center of dilation. So it would be recentered at the origin, then multiplying the coordinates by the scale factor because that's our rule for when we're centered at the origin, and then adding the center back. You can do it that way, but doing it graphically is just a whole lot easier and saves a whole lot of time. For the next one, before I write down and show you guys the answer, I want to talk about some of the incorrect things that people were doing. So some people were saying that we could reflect over point Z. So people were saying to reflect over this point over here over point Z. So I just put a line through point Z. The problem is that in the question, they tell you what's supposed to correspond to what. So we know from the names of the triangles that X is supposed to, let me get a marker here, that X is supposed to correspond to U, that Y is supposed to correspond to V, and that Z is supposed to correspond to itself. But if you take this triangle and you flip it over the line, it'll look something like this. And since it's mirror images, point X will be over here and point Y will be over here. See, a lot of people, they didn't actually draw this. They were like thinking this, but they didn't actually draw it. So notice, then if you turn it and make it bigger, X will match up with V if you turn it and make it bigger. But X is not supposed to match up with V. X is supposed to match up with U. And Y is going to match up with U, but Y is not supposed to match up with U. Y is supposed to match up with V according to the naming. So if you flip it, it actually messes up the orientation. So a reflection is not going to be helpful here. So I just wanted to point that out. What we do need to do is we do need to rotate it because it does need to be turned. They're not facing the same direction now. And when you're talking about the rotation, before I show this written up afterwards, you do need to specify as much as you can. So I don't know exactly the angle that we're rotating here. A lot of people were writing down 90 degrees, 180 degrees. I saw some other angle measurements written down there, but we don't have a grid. We don't have coordinates. So we don't know what's actually happening to each of the points. We don't know what kind of rotation is actually happening. So if I want to rotate from here to here, I can get as specific as I can. So I'm going to say a rotation clockwise. That would be a clockwise direction. You can also say counterclockwise as long as you describe it. And I will write down an explanation afterwards so that you can see how to best describe this rotation. But I just want to mention the overall components that need to go into it. So the direction and the center. And our center of rotation is the point that we're going to be rotating around. So that's going to stay where it is, and the whole shape is going to be rotating around it. So since Z needs to match up with Z, Z is already in the right spot, right? Z is connected to itself on the other triangle. It matches up to itself. So I want Z to be my center of rotation because then everything is going to rotate around point Z. The whole triangle is going to rotate around point Z. But even though the triangle is going to turn, Z is still going to stay up here at the top where it's supposed to be so that it could align with Z from the other triangle. So I just want this to stay the same and the whole triangle to rotate around it. So point Z is going to be my center of rotation here. So now if you take this and you rotate it, I'm going to try to draw a picture. I'm trying to draw about the same size as the original. So when you turn it, Y is going to go over here and X is going to go over here. Let's just make sure that's good so far with orientation. Is Y supposed to match up with V? Yes, that's all good. Is X supposed to match up with U? Yes, that's all good to go. So then from here, we do need to dilate it. And there's two main clues that we are going to need to have a dilation. The first is that this triangle is clearly bigger than this triangle. So something about the size is going to have to change, right? This one's going to have to increase to become this one, or this one's going to have to decrease to become this one. But I'm describing from here to here. So I'm going to write that it's going to be made bigger. Um, Also, it's a similarity transformations. And we know that all of the other transformations, reflections, rotations, and translations are rigid motions. They make congruent figures, not similar figures. So if it's talking about similarity transformations, it's going to be talking about a dilation. So I am going to have to describe a dilation here. Now, I know that we don't have numbers here and we can't find the exact scale factor that we're going to be dilating by, but we're going to try our best to describe it using the information that we have here. We also need to mention our center of dilation because remember, dilations also have centers just like rotations. Just like over here in this last question that we did, we have a center of dilation that was not the origin, but we have a center of dilation. So we need to mention what our center of dilation is. Our center of dilation is also going to be point Z because just like with a rotation, if that's the point that we're dilating at, that means all of the other points are moving away, a certain distance away from that center if we're making it bigger, or towards that center if we're making it smaller. So the center of dilation is going to stay where it is, and everything else is going to move either away from it or towards it to make it bigger or smaller. So since Z is already where it's supposed to be, since it's already matched up with itself, that is going to be our center of dilation, and everything else is going to move away from it to make the triangle bigger. I'm going to take a second and I'm just going to write up my response and then we can take a look at it. And I was super, super lenient on the grading of this one. I gave half credit if you just mentioned rotation and dilation. But here is a complete answer that I have. And it doesn't have to be this exact wording, but here's a complete answer. Rotate triangle XYZ clockwise about point Z, so with the center of rotation at point Z, so that ZX coincides with ZU, ZY coincides with ZV, and angle Z matches up to angle Z. That describes how we're rotating it without specifying an angle measurement. Then dilate triangle XYZ centered at point Z by a scale factor of ZU over ZX. You could have also used by a scale factor of VU over YX or a scale factor of ZV over ZY. Because remember, scale factor is image divided by pre-image. So if I take a side from the bigger triangle, aside from the image, divided by the smaller side, corresponding side from the pre-image, then that should give me the scale factor. And that scale factor holds for all three pairs of corresponding sides because dilations make similar triangles, which are proportional by the same scale factor. So then I just wrote here because it did say that shows the triangles are similar. And having a dilation in your sequence already shows that because a dilation makes similar figures. But I just wrote to be super clear, dilations preserve angle measurement and make proportional sides so the triangles are similar. Okay, here we have to construct the line of reflection. So what we're going to do is we're just going to connect to pre-image and their corresponding image points together. And let me get my compass. And I'm going to just make perpendicular bisectors because remember the line of reflection is equidistant from the two figures. So we just want to go more than halfway down. It doesn't matter exactly how much. Arc above and below. Then I'm going to take my compass and I'm going to move over to the other endpoint of the line segment. And without changing the length, I'm going to do the same arc. Here we go. Now to be super, super, super accurate, we should also do the perpendicular bisector of the other line segment. And I didn't take off points for this on the test. It should end up being the same line of reflection because it's one line of reflection that this figure was reflected over. But just to be super, super accurate, we should also do for a second pair of pre-image and corresponding image points. So there's our first arc, and then here is our second arc. And if I connect through with my line, notice how it is the same exact line of reflection. And now it's super, super, super accurate. To get even more accuracy, we could do the third pair of pre-image and corresponding image points, but 2 is good enough. Okay, for this one, everyone was getting this wrong because when you see this dot symbol, remember the order matters. So we read it backwards. So this is first, the translation, and the reflection second. A lot of people were also thinking this was a rotation. So small r is a reflection, but if you didn't remember, for rotation, you need an angle measurement that you're rotating by. For reflection, they'll give you the line of reflection. The x-axis is a line, so that's the line of reflection. So that's another way to tell that it was a reflection. So I'm just going to graph my original points. 1, 2, 3, 4, 5, 6. 1, 2, 3. And notice how it says the use of the axes is optional, so you don't have to use this. You could do it all mathematically, but you do at the end need to state and label the coordinates. And a lot of people who did it graphically didn't actually write their coordinates down at the end. I didn't take off points for that, but on the Regents exam, you're not going to get credit for anything that's on the graph if it's optional. You're only going to get credit for the points that you write down on the paper. So if you don't write down anything on the paper, then you're not going to get credit at all for anything. Okay, -1. Let me get the same color. -1, 1, 2, 3. So that is, oops, why am I labeling it that? It's the original one. There we go. -2, -1, and -4, -1. Let me connect that together. And I'm just going to do this graphically because it's just so much easier to do graphically. You just avoid so many mistakes doing this graphically. Maybe not because I'm doing it on the computer, but generally, let me make this a little bit bigger. You avoid a lot of the mistakes doing it graphically. There we go. Can see that better. Okay, so first up is the translation, and it is 7, 5. Remember, the first number is on the x-axis, so that means 7 to the right because it's positive, and 5 up because that's the y-axis and it's also positive. So let me move everything 7 to the right. 1, 2, 3, 4, 5, 6, 7, and 5 up. 1, 2, 3, 4, 5. So this is A prime. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. This is M prime. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. This is T prime. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And this is H prime. So now already I got the translation done. Let me just connect this all together. Okay, and then finally, I just need to reflect over the x-axis. So let me just mark our line of reflection. So the x-axis is here. A lot of people were mistakenly reflecting over the y-axis instead of the x-axis. So remember, when you reflect over a line, it's mirror images. You want equal distance from each of the points to the line of reflection. So from point A prime to the line is 1, 2. So I'm going to move 1, 2 on the other side of the line, and I'll just label it A double prime. Okay, to the line of reflection from T prime, it's 1, 2, 3, 4. 1, 2, 3, 4 on the other side of the line. That's right here. I just don't want to confuse myself as to where it is. Okay, H prime, 1, 2, 3, 4. 1, 2, 3, 4. Right here. It's hard to dot things on the computer. 1, 2, 1, 2. I forgot my double primes here. There we go. Let me connect together. But I would get no credit on this question if I left my answer the way it is. Remember, what I have to do is actually write down the coordinates, because right now this would receive no credit. So let me write down my coordinates, and they have to be labeled, so now they're labeled. M prime is 1, -2. A prime is 1, 2, 3, 4, 5, 6, -2. T prime is 5, -1, -4. And H prime is 2, 3, 1, 2, 3, 4, 3, -4. And those are the coordinates of the points. Super simple to do this graphically. Are the pre-image and image after the sequence of transformations congruent to each other? Yes, they are congruent. Oh, this is not the rotation. My bad. reflections and translations are rigid motions. They preserve angle, measure, and side lengths, so they make congruent. Oh, this is not the triangle here. My bad. They make congruent figures. This is a four-sided shape here. Okay, and the last question. That was the last question, right? Let me see. Yeah, I didn't miss anything. Okay, and the last question, we're going to dilate this triangle by a scale factor of 3. So we're going to be making this triangle 3 times bigger. And the way that we're going to do that is we're going to take each of these points and we're going to move them 3 times the distance from point A as they already are. So what I'm going to do first, and let me make sure this is black. There we go. I'm just going to connect through my center of dilation, my pre-image point, and I'm going to go pretty far out because I don't know exactly where the image point's going to be, but D3 is pretty big. And that's because the center of dilation, the pre-image point, and the image point are all collinear. They should all lie along the same line. I have to zoom this out again because for the graph, it made it easier, but for constructions, it makes it harder. I'm going to do the same thing with point A and Z because the center, the pre-image point, and the image point will all lie on the same line. And I'm going to do the same thing with A and Y because once again, the center of dilation, the pre-image point, and the image point will all lie along the same line. And I'm trying to make this as accurate as possible, but on the computer, it's a little bit difficult. Okay, so what I'm going to do is I'm not just going to randomly start making marks. What I'm doing here is I'm putting my endpoint on point A. And what I want to do is I want to measure the distance that point X is from the center of dilation, point A. So I want to open or find the hole that matches up to point X as best as I can. And then I'm going to make an arc to show that I measured. If I don't show that I measured, then the person grading your Regents exam might think that you're just using some random measurement on your compass to make these arcs. But if you actually measured, you should put an arc to show that you measured, which is what you're supposed to do. Okay, then I'm going to put it over here. So that is the distance. Now, if I repeat the distance, I'm doubling it. And then if I repeat it again, I'm tripling it. And that's what I need. I need 3 times the distance from the center that it currently is. So that would be the point X prime. Okay, now I'm just going to repeat for the other points on the triangle. So I'm going to go over to the center of dilation. And once again, I'm going to measure to the first pre-image point, to point Z, and I'm going to put a little arc to show that I measured, that I'm not just, randomly guessing how big that distance is. And then I'm going to double the distance. And then I'm going to triple that distance. There we go. And that is the point Z prime. And then finally, I'm going to go over, let me get a different color. I'm going to go over to the center of dilation once again, and I'm going to measure the distance that point Y is from it. Okay, that's accurate enough. There we go. Okay, now I'm going to double that distance, and then I'm going to triple it. And there I have the point Y prime. So now I've dilated all of my 3 points by a scale factor of 3. All I need to do is connect my image points together. So connect, connect, and connect. and my triangle appears to be 3 times as big as the original one.